Hello? Okay, good. Good.
It is a pleasure today to have the presentation of Albert Gaiebi that joined the University of the Balearic Island. Is not in our institute, it is the University of Balearic Island and also IAC3. I never told you the English name.
Yeah, that one.
Today is presenting us his activity on this supersolidity that is a pretty recent phenomenon. It's been studied in different groups. So Albert got his PhD in 2017.
Correct.
And it was at the University of Barcelona. And then he has been actually traveling a lot
Yes.
in different institutions. So he was in Trento, Newcastle,
Yeah.
Hanover,
and now here.
and now here. And so now he's aiutante dottore, I understand, of the university. And the floor is yours. I asked him to have a very, let's say, broad introduction about the topic. Okay? Thank you.
Okay, thank you very much. So today I want to talk about this work that I've been doing in the last, let's say, couple of years, maybe a little bit less, in the group of Luis Santos in Hanover. And here, Daniel Sherman was the PhD. I was just the postdoc there, and we were studying double supersolidity, which, and of course, I mean, in order to know what is a double supersolid, we first need to know what is a supersolid, right? And and therefore, I will start with a very broad introduction of what is a supersolid, starting first with Bose-Einstein condensation and so on, escalating up to supersolidity, and then to all the theoretical work. And at the end, I will mention a current work that that we are doing with in the group of Jean Dalibard in Paris, in which we have a joint collaboration theory experiment that is working pretty well. So let's start first with a little bit of history of BC. BC is something that was first predicted in 1924 by both Bose and Einstein. And they just showed that there should be a transition below a certain temperature below which all the particles should, especially if they are bosons, should occupy the single particle ground state. So this should become macroscopically occupied. And this kind of a state is a Bose-Einstein condensate. Here you can see this kind of figure. This was developed by Wolfgang Ketterle. He was one of the discoverers. I will tell you about that in the next slide. But here you can see that when you have a very high temperature, all these particles just behave very classically. They are like billiard balls, or they just move with a very well-defined velocity. But then when you start to lower the temperature more and more, then they start to, you start to see the wave behavior of these particles, which is the Broglie wavelength, and then the Broglie wavelength starts to become bigger and bigger and bigger until it becomes something of the size of the system itself, and they start to overlap more and more until you get what is called the Bose-Einstein condensate, which you can understand as a giant matter wave. And Bose-Einstein condensation is a phenomenon that is linked to other phenomena. One of them is called superfluidity, which is something that was first observed in superfluid helium, right? And here you can see that this is the typical figure that you can see when you put in your Google superfluid. You get this, and this is essentially a helium. There is here you have this kind of glass with helium inside. And you can see that this helium is just falling down through the glass. This means that this helium is like escalating the wall and then going down. This escalation of the wall happens due to capillarity effects, right? And then due to the fact that the system is a superfluid, and superfluid means that it flows without viscosity, it can actually do that without dissipating any energy. And then just because of potential energy, it just falls down and decays. And the other one is global coherence, which here I just put a picture of something that I'm very familiar with since I've been doing this for many years. And also because global coherence is something that happens when you start when you have all the particles and they are all of them doing the same. Here, like in a choir, when you have all the singers singing at the same tune, hopefully. But up to then, up to here, everything was just a prediction by both Bose and Einstein. It wasn't until 2001 in which Eric Cornell, Wolfgang Ketterle, and Carl Beeman were awarded the Nobel Prize for an experiment that they actually realized in 1995, which is the year in which Bose-Einstein condensation was actually discovered. And here you can see that in their experiment, they just show this is the measurement of the momentum distribution of the system. And you can see that when the temperature is high, it's actually above this critical temperature, you have a distribution that resembles more the Boltzmann-like distribution. But then when you start to lower the temperature more and more, you start to have a distribution that develops a peak at around k equals 0. And this is precisely the indication that you start to occupy, to populate macroscopically the single particle ground state. But this was Bose-Einstein condensation. I talked about superfluidity, but my presentation is about supersolidity, which is something different. Before I said that the superfluid is a fluid that can flow without viscosity, and then, of course, all of us know what is a solid, right? Just a solid is a system that presents a crystalline order. And supersolid is just the fusion of the words superfluid and solid, which means that a supersolid is a solid that can flow without viscosity. And here is when you ask, what does it even mean? Yeah, it actually has a meaning, but I will tell you later. Let me first just announce the fact that supersolidity was found experimentally in 2019 in a system that was based in dipolar atoms. However, maybe some of you recall in 2004 that there was an experiment in superfluid, just in helium by Moses Chan, in which they claimed to have found a super solid helium, but it was actually proved to be wrong in 2011. I mean, I can tell you after the talk more details if you are interested in. But what is so cool about these dipolar atoms? Why can these atoms become super solid eventually? First, let me explain how these dipolar atoms, let's say, work. Because we need to know first that dipolar atoms have two different channels of interaction. One is the contact interaction, right? And the other one is the dipolar interaction, which is long range and anisotropic. So we have one that is contact, which is just point-like. If they are in the same position, they interact, and if they are not, they don't interact. And the other one, which is dipolar, means that they just behave like magnets. So they have an associated dipole. If they are in a head-to-tail configuration, they attract each other, and if they are in a side-by-side configuration, they repel each other. And here you can see this is the typical dipole potential. Maybe you have seen this in electrostatics and here you can see exactly this phenomenon in which when they are in the head to tail, they are attractive, in side by side, they are repulsive. But then there is an extra element here, which is what is called quantum fluctuation. And here we say, here comes the magic, because I'm not going to explain what is the origin of this term. But I can tell you that these kind of quantum fluctuations that actually stem from the fact of the energy of the vacuum, this has a dependence on the density that scales differently from the mean field energy. The mean field energy is just the energy that scales with the interaction, and the interaction is just two particle interaction, which means that it must scale with the density to the square. However, when you have quantum fluctuations, this scales as the density to the 5/2. This was first developed in 1957, I believe, by Li, Wang, and Yang, in which they did what was called the Li-Wang-Yang correction to the mean field energy. This was just for a single contact interacting gas. This term is slightly different for the case of dipolar Bose-Einstein condensates, because it's not just contact interaction, you also have dipolar interaction. But this condition of energy scaling with the density to the 5 halves holds. And now coming back to the experiment, I said before that dipolar or dipolar supersolids were found in 2019. This was done simultaneously in 3 places. One is Stuttgart, Innsbruck, and Pisa. It was in Stuttgart by the group of Tillman Fau, then in Innsbruck by the group of Francesca Ferlaino, and in Pisa by Giovanni Modugno. And here you can see that when you have I mean, when you do the time of flight expansion, and doing time of flight means to take your gas and to let it expand. When you let it expand, you start to magnify the frequency components of this system, right? Because it evolves according to the velocities. And therefore, you can map this to what is the so-called the momentum distribution of your gas. And you can see here 2 peaks, right? You have one central peak, right, which is just the zero momentum. But you also have 2 finite peaks, which means that you have a certain periodicity, right? Which means this crystalline order of the supersolid. I will focus more just now why this appears. And first I will explain about this. This was what is called the energy spectrum. And for a normal contact interacting gas, this energy spectrum is what is called the Bogoliubov spectrum, or the original one, which has something that has a certain slope, is linear at a small momenta, and then it's quadratic at very large momenta. Right? At large momenta, you have essentially the free dispersion. But when you have a dipolar gas, the dipolar gas develops here a minima. This is what is called a roton. This receives the name of a roton. And now let me talk about the Goldstone theorem, because this is something that probably you have heard about, but maybe you are not fully familiar with it. The Goldstone theorem states that a system will present a Goldstone mode. I will explain what a Goldstone mode is for every spontaneously broken continuous symmetry. A Goldstone mode is a mode that is essentially gapless when you go to a small momenta. And so when you break when you spontaneously break a continuous symmetry, and my apologies, the system will develop another Goldstone mode. And this is, for example, what happens here. Here, there is something that you can deal with some parameters. For example, when you increase or decrease the contact interaction by means of the so-called this wave scattering length, you can essentially bring this minimum down and down until it eventually clashes this point. At this point, this is historically known at the point in which the dipolar gas becomes unstable. But this is actually not what happens. And this doesn't happen because remember when I said before about the quantum fluctuations that scale with the density to the 5 halves? This term is actually always positive. It's defined positive. It's always positive, which means that when you start to collapse, because this is a negative energy, you start to collapse, the system starts to implode, but it cannot implode infinitely, because if it implodes, the density increases, the Lagrangian correction or the quantum fluctuation starts to play a bigger role, and it stops the collapse. So this eventually this eventually stops this collapse, and you get something that is stable. And this is exactly what happens here. When this clashes zero, you start to make free the population or the development of something that has a certain wavelength, right? Which is this one. Which means that you start to develop this kind of periodicity, right? This is precisely the solid part. And then when this happens, this actually defines in solid state physics what is called a Brillouin zone. This defines an effective Brillouin zone, and therefore from here you can start to fold, right, your spectrum again and again, and you get a spectrum like in solid state physics. When this happens, you can see here that the number of modes here doubled, which is exactly the Goldstone theorem, right? Because you broke spontaneously 2 symmetries. Which are these 2 symmetries? The first one, which is always present, is the symmetry of the phase. Remember that the phase is arbitrary in a quantum system, which means that choosing a certain phase breaks spontaneously the symmetry of the phase, the continuous symmetry of the phase. But then you have the other one, which is translational invariance. Translational invariance is broken when you put modulation in real space. Therefore, you have two Goldstone modes. But what happens when you start to increase more and more and more the importance of the dipolar interaction with respect to the contact interaction? Eventually, you will see that one of these modes disappears and you only left with one. At this point, you see that you still have periodicity, right? Which means that the spontaneous symmetry of the translational invariance is still broken. But what you broke is the fact that you no longer have a global phase. The global phase is broken, which means that these different droplets that you have created are completely incoherent. This defines three different regimes in your system. The first one is what is called the superfluid regime. Also, other people I will call it here also the unmodulated regime for obvious reasons. It's unmodulated, has no modulation. Then this one is actually the supersolid regime. This is supersolid because it has both solid part, right? Because you have some modulation in real space, and you have also superfluidity that comes from the fact that you have a global coherence between the different droplets, right? Because remember that here you have two Goldstone modes, which means that you have a global phase. And therefore, this ensures superfluidity along the whole chain. And then here, this is what is called the individual droplet regime or the crystal regime. It receives several names. How can you prove that? There have been several experiments on this kind of supersolid so far in the last 7 years or 6 years, because 2026 barely started. And here you can see that this is an experiment that was done in the group of Giovanni Modugno in Pisa, in which they took their supersolid and compressed it. They compressed the supersolid, and when they compress the supersolid, they see that in the unmodulated regime, they also called it the BEC regime, everything just reacts with a single frequency. They just were measuring the width of your system, right, which was oscillating, right? If you compress it, it starts to oscillate, and it oscillates at a single frequency. The frequency of oscillation is just one, which is this one. But then, when you enter in the supersolid regime, you start to see a beating between two frequencies. There is a beating, and when they just did the Fourier analysis, they found two frequencies, and one of them was going up, the other was going down. These lines are just the theoretical models. There is the one that was predicted theoretically, and you see that it matches pretty well. This was one of the very first experiments, but you can see that one goes up and the other one goes down. Precisely the one that goes down and eventually disappears is the one that corresponds to the superfluidity, right? Because remember that later we go into the individual droplet regime or the crystal regime, in which the coherence between the different droplets is broken, and therefore you don't have superfluidity between the, you don't have any kind of global, yes?
How can you connect this plot about the frequency of oscillation of the condensate that's been compressed with the previous graph that was actually the dispersion relation, also maybe middle of K was the previous one. So I'm failing in connecting what you show here with the one that was really.
Well, one is homogeneous, but here you are you are just taking your. I mean, imagine that you have that you take your system. This is completely finite. I mean, you have like a dispersion relation in homogeneous space, and then you have the excitation spectrum in a finite system. That you start to have like the breathing mode, the dipolar mode, or the cone. Probably you know the cone mode or the cone sham, in which.
The other one is obtained in sizes.
Yes, exactly. They are different. They are different because one. Wait, check. There is the wavelength. There is the wavelength because the wavelength is well defined in an infinite system. In the other case, this is the epsilon d. The epsilon dV measures the ratio between the dipolar interaction and the contact interaction. Exactly, yeah. It's completely different, yeah. I mean, but this actually shows that when you increase the dipolar interaction more and more and more and more, or equivalently, you just reduce the contact interaction, because this is actually what they do in the experiment. they can go from the BC to the supersolid to the crystal. And there have been also the study of other kind of excitations, such as the scissors mode. The scissors mode is the one in which you take the supersolid and you start to do this kind of scissors movement. And it evolves to a different kind of excitation spectrum. And I mean, we did a work that was also done by Giovanni Modugno later, that was published later in Science to measure the superfluid fraction of a supersolid, which was pretty interesting, but also very conflictive. And then this is pretty recent. This is from 2024, if I'm not wrong, or at the end of 2024, in the group of Francesca Ferlaino in Innsbruck, in which they managed to excite vortices inside a supersolid. Because remember, these are quantized superfluid vortices. Remember that supersolids, they are not fully superfluid, that they are at least partially superfluid, which means that they can hold superfluid vortices. And this is what they show here. But this was just the introduction in order to see more or less where this work is framed in. And now let's go with the with the outline. And for this outline, we will first go with the theoretical model that we used. And then I will focus both in the case of double supersolidity with symmetric interactions and asymmetric interactions. And you will see that they are very interestingly different. Yes.
I mean, the real density of the system is still homogeneous.
No, the density is not homogeneous. Even in the infinite one. I mean, in the infinite you have modulation, but also in the finite you start to have modulation. However, it is true that in the finite, and this is probably something that can be a little bit, let's say, conflictive in the sense that many people call it a supersolid, which means that it's partially solid, but in reality, in experiments, they manage to do like 3-4 droplets only, which means it's like a solid with only 3-4 droplets, which many people say it's maybe you need more in order to call it a solid, but it's true that in an infinite case, you would get a solid, because I mean, in the experiment, this is what you get. In the theory, this is what you get. But the problem is that in the experiment, they cannot make it bigger than that. And what is the kind of model that we use for that? What we use is what is called the Gross-Peters equation, but not the normal one, but we use what is called the extended Gross-Peters equation. This is just the Schrödinger equation with this kind of Hamiltonian, which is a nonlinear one, which you have here the kinetic energy, you have the trap, and you have here these two terms, and these two terms are the ones that are a little bit different. Let's go with the fourth one first. This one is just the interaction. And here, remember that there are two channels of interactions, the contact interaction and the dipolar interaction. This term is accounting for both. And here you can see that it is nonlinear. It depends on the square of the wave function, because this term is just a two-body interaction. And then we have this term. This term is the quantum fluctuations. Remember, LHY stands for Li, Huang, and Yang. Li, Huang, Yang correction, which depends on the density, and it takes a rather complicated form. It comes from this energy functional. This is the energy functional corresponding to the quantum fluctuations, and this is the chemical potential. Remember, the chemical potential is the derivative of the energy with respect to the density. And here you can see that this energy actually scales with the density to the 5/2. You can see here this depends on this to the 5/2, and this is linear to the density in a very complicated way, but it's linear to the density. And what we do is to simulate this equation, and the first thing that we do is to find the ground state, which is the ground state of this equation. And we find a pretty rich phase diagram. And here I'm showing the phase diagram for the case of asymmetric interactions, which means that the interactions between particles in one of the components is different from the particles in the other component. And with this, let me remember that we have two components here, because everything here was just with one component. It was just one supersolid. But In the title, it was saying double supersolidity. We call it double supersolidity because we are using two components, and these two components can become supersolid, maybe at the same time, maybe not. We don't know, but this is the goal of the work. Yes, exactly. For us, we were assuming the case of two different hyperfine components of dysprosium. Dysprosium is a very highly dipolar atom. Actually, it's so far from all the atoms that have been condensed, is the one that is that has a higher dipole moment. It's a 10 Bohr magneton. Then there are others that are pretty good, with erbium with 7 Bohr magneton or chromium with 6. But dysprosium is the most popular one for this kind of experiments because remember that these kind of states happen when when the dipolar interaction becomes important with respect to the contact interaction, and the highest the dipole moment, the better. That's why dysprosium is very, very good for this.
I suppose that you need the configuration to have the pulse dipolar interaction.
Well, I mean, it's what do you mean repulsive? I mean, dipolar interaction is attractive or repulsive depending. Thank you. I forgot to mention that. Yes. I mean, the word that you're looking for is polarized. What we do is to apply a magnetic field in such a way that we polarize all the atoms in the direction that is transversal to the direction in which the translational symmetry is broken. So if the translational symmetry is broken along X, the polarization direction is perpendicular to it. So Y or Z, or a combination of it. Is in such a way that they repel each other. Exactly. Thank you very much. So, and it's a cigar. Okay, maybe it's better if I draw it. Yeah. I mean, you put everything like in an elongated cigar, but here this doesn't mean that the system is 1D because the transversal. The transversal direction matters a lot, right? Because first of all, Y and Z are not equivalent, right? Because one has the polarization direction and the other hasn't. So you really need to consider the 3 dimensions here, which means that here all the calculations are full 3D, and you really need it. Are there any other questions? Okay. If not, this is the phase diagram that we found, and here you can see that when the interactions are, this is A12. A12 is the contact interaction, the S-wave scattering length between atoms in component 1 and component 2, right? There is the interaction between atoms in component 1 and 2. And here you can see that when this interaction starts to become big, you go to this modulated regime or the B0 regime. Everything is just not modulated. And you get something like this. Then eventually you enter into what is called the double supersolid, in which both systems simultaneously become supersolid. And this is actually very interesting because the first question is, why do they become simultaneously supersolid, right? I mean, one could become supersolid before the other, but they don't. And the reason is something that was already found like the year before. It's the phenomenon called catalyzation, which means that supersolidity catalyzes supersolidity. Okay. And when you have a double supersolid, then you can try to go more into the individual droplet regime or the crystal regime. And here you actually see that the two components can crystallize, can break coherence independently. This is a phenomenon that doesn't catalyze. So crystallization doesn't catalyze crystallization, but supersolidity catalyzes supersolidity. And now this was just the ground state. Now we want to see what happens in when we have this ground state and we excite it. We just excited, like for example, in the experiment of the compressional oscillations that we were compressing, and this produces excitations. And in order to study this kind of a spectrum, what we need to solve is what is called the Bogoliubov excitations. And for this, one just assumes some excitations over the ground state in this way. And one ends up with this kind of matrix, which here it looks like a 4 times 4 matrix, but remember it is 4 times 4 times all the points in the grid, which can be 1,000,000. So this is a rather big matrix that it took for us of the order of 1 year to diagonalize. And yes, it was painful, but we managed. And here there are just expressions for these different parts of the matrix. It's a little bit complicated, but can be calculated analytically. And you can also try to simplify a little bit this equation by this kind of transformation into these functions f and u, sorry, f plus and f minus. And this is actually very important because these f plus and f minus are actually very intimately connected to the fluctuations of both the density and the spin. And here we'll connect to the next slide. I believe it's the next slide. No, not the next one, which is the fact that when you have two components, you can have two pictures, because with two components we can think excitations in component 1 and excitations in component 2, but you can also think on excitations in the density channel and excitations in the spin channel, right? So you can you will need to understand all the excitations from the two perspectives. And first of all, I wanted just to put this reminder that excitations in trapped supersolids have been extremely important. This is the best way to test supersolid behavior in a supersolid, and this has been done repeatedly in many papers, such as this work with the group of Francesca Ferlaino. This was done in the group of Tillman-Fau. These two papers were almost simultaneous, but you can see that the kind of results that they get are very similar. They obtain very similar results. This is a much recent one. This is 2024, in which they did the same but in a ring. This was in the group of Tillman-Fau, but in collaboration with the group in Sweden, Steffi Reinman. And what I said before is how to characterize this eigenmode, right? Remember that we had this U and B that we were moving to the F plus and the F minus, which are these ones. And these F plus and F minus are just related, but one is connected to the fluctuations in the density in this way. Actually, F minus is connected to the fluctuations in the density. And with these fluctuations in the density, let's say 1 or 2, right? This sigma accounts for the component 1 or component 2. And from here, you can see fluctuations in the density channel or the spin channel. And from here, and these expressions also with of S plus, S minus, and S sigma, you can define two quantities, which are P and Q, which these quantities are very interesting because, first of all, they are defined between -1 and 1. Which they are just a scalar, and P indicates whether the mode is in component 1, so it's just exciting component 1, in which it will take the value of 1, or it will be in component 2, in which it will take the value -1. And Q will be the same between -1 and 1, but it will be, for the density channel, will be 1, and the spin channel will be -1. And now let's go to the case of symmetric interactions. Remember in the outline that I mentioned that I was going to study in a separate way both the symmetric case and the asymmetric case. Symmetric interactions means that the interactions in component 1 and component 2 are exactly the same, right? And if they are exactly the same, this means that you can do some approximations. For example, the scattering length in 1, 1 is 2 is the same, the atom number in 1 and 2 is the same. This is the chemical potential in 1 and 2 is the same, and so on. And from here, we get this kind of result that actually connects very well with this kind of result. This is the one that I presented before. It's just here. It's just this one. This is the the one done by the group of Tillman-Fau. This is the one of Francesca Ferlaino. And this corresponds exactly to this case. We used exactly the same parameters that they use, so we match perfectly. But with one difference, because here you can see, maybe it's better if I use the. Okay, I don't want to. But for example, here you can see that one mode that is completely flat, that has exactly the value of 1. This is the value of the frequency of the trap. This is the dipole mode. This is when you have your system in the trap and you just displace it and it starts to oscillate like this, and it oscillates exactly at the frequency of the trap. And then you also have this kind of mode here. This mode of here is the breathing. It takes more or less this value. It is the one that like this. This is the breathing mode, and we find them exactly the same, right? This is the dipole trap here, value 1. You have here the breathing, and we also did the calculation in the color behind, in which we take our system and we make it to breathe. And when you make it to breathe, you start to realize that you excite the breathing mode here, right, which is these green dots, and then it splits. Remember when I mentioned that in a single component you were also splitting between the superfluid part and the part of the solid, that they were excited at different frequencies. That is exactly what happens here. You have one that goes up. This is the one corresponding to the crystal one, and then here you have 2, right? In this case, we have 2 because for this kind of parameters, instead of, because in the experiment of Giovanni Modugno that I showed before, they had a crystal with only 2 droplets. So these are a very minimal crystal. Here we have 3 droplets, which means that we have actually 2 instead of 3. Instead of 1, sorry. We have here 2 modes that go down instead of 1 like before. But let's go now to asymmetric interaction, and we have this. This was the one that took more than a year to calculate, but it's incredibly rich. First of all, here in both the left and in these 2, these 2 correspond to the even modes. So these are modes that have even symmetry in the trap. So we are just putting a trap, and there are modes that have even symmetry, and there are modes that have odd symmetry. And in order to make this thing readable and not to overlap everything, we just decided to separate the plots. And these are the even modes. These are the odd modes. These 2 are plotted according to this scalar P, that, remember, if P is equal 1, one has the excitation lives in component 1, and if P is minus 1, it lives in component 2. And Q is the same, but for the density and the spin. If Q is 1, it lives in component 1, and if Q is minus 1, it lives in the, if Q is 1, it lives in the spin, in the density channel, and if Q is minus 1, it lives in the spin channel. So here you can already see that here the most important, okay, just as a check, you can see here that we have a completely density mode with frequency 1. This is again the dipole mode. This is actually very interesting because this means that regardless of the, this means that regardless of the interactions, of the asymmetry in the interactions, the dipole mode will always take the same value, the value of the frequency of the trap, and it will be 1, and it lives in the density channel as it should be, just the density mode. Then what happens when with this mode? This mode is also density mode. This is the breathing mode. Remember that the breathing mode now appears here and not here because the breathing mode is an even mode. It's not odd, so it's in the upper panel. And it takes this value. And then here you start to see a lot of things. And this is exactly when you go from the unmodulated to the supersolid. In the transition from the unmodulated to the supersolid, you have this, and you have one mode that goes very, very, very fast down. Here we have a zoom here, but we have this mode that goes very, very fast down. And remember, this mode that goes very, very, very fast down is precisely the mode that corresponds to the roton. Remember in the dispersion relation, right? That we have a roton and the roton was going down in order to break to define this effective Brillouin zone and folding your spectrum, right? This is precisely this mode that is going down. And when you arrive here, you have what is called the Higgs mode. But now let's focus at what happens after. What happens after, and then we have to move here, because here, for example, you see this is the even part, right? And you have essentially three modes, right? So there is, for example, what you would see if you excited the breathing mode, because the breathing is even, so you would only see things that are in the upper panels. And here you see that you have one that is completely green here, which means that this is a density mode, this one. But then here you have two modes, and these two modes are, one is 1 and the other is -1, which means that this mode is a mode in component that lives in component 1, and the other mode is a mode that lives in component 2. And it eventually, they essentially go down. Remember that when you put the, I mean, when you do the compressional excitations, you had the modes that were going down, and eventually they were crashing into the crystal, right? And they were disappearing. But remember in the phase diagram that I showed that supersolidity was catalyzing supersolidity, but crystallization was not catalyzing crystallization. This means that the two components should go down differently, and this is exactly what we see here. One is going down faster than the other. That's why one component is crystallizing before the other. This is exactly the kind of things that you observe here. And from here, now we can study this Goldstone mode. Sorry, I didn't mention the Goldstone mode, but the Goldstone mode is just this one that lives here. It's the one at very small energy, but I will comment now in this slide. I mean, first of all, you have this Goldstone mode. This Goldstone mode is a mode in which you have this kind of density. This is the kind of state that we have here. This is just the density. And this is the dashed line, and then the other one is the eigen mode. And you see that this state is just doing like this, right? This is an odd mode. Remember, it's here. It's in the bottom panel. This is an odd mode. But then you have here this Higgs mode. In this Higgs mode, you see that you have like the amplitude mode, right? So you have more something like this. And when you start to see the dependence in time, you see that there are different modes, like for example, the dipole mode that I mentioned, the one with frequency 1, and it essentially has the same frequency for the two components, right? And it just evolves in time. Then you have the spin dipole mode. The spin dipole mode, it's a mode that lives in the spin channel, and it's this one, right? This is because it's completely blue, -1 corresponds to the spin. And when you see, you can see that the two components evolve differently. And then you also can do the same for the supersolid Goldstone. The supersolid Goldstone has a much smaller frequency. It's this one. The frequency is very small, so it evolves very slowly. But there's something very interesting, because here you can see that the supersolid Goldstone, the two components are evolving in phase. But here it looks like they are evolving out of phase, right? Because it's like this, right? There is one component and the other, there is the other. So when one goes like this, the other goes in the opposite direction, which means that this is actually what they are doing around this position, but actually there is a center of mass movement that is compensating for it in order to make the Goldstone mode to evolve in phase. And now for the axial breathing modes, which are these ones, right? The one going here and these ones. These are the axial breathing modes. These are the ones that you would observe if you did in an experiment the excitation of your double supersolid. And actually, you would observe something very interesting, because if you measure the signal independently in component 1 and in component 2, you would observe in one that here you have a signal, right? Because it's a modulated phase. Here you would have the transition into the double supersolid. And you would see this one that is completely in the density. So it should appear in both components. And it is exactly what you see, right? It appears in both, but then you have the two going down, that one was in component 1 and the other was in component 2. So one should appear only in component 1 and the other should appear only in component 2. And this is exactly what you observe. If you did this in an experiment, this is what you would observe. And this actually proves that in a double supersolid, the superfluid fraction of the two components is different, which is something that was not known. And it was very interesting because we did this paper when we published it like at some point. I don't remember exactly at which time we published it, but like 1 week after another paper was published by the group of Jan Dalibart, in which they built exactly the experiment that was designed in order to do our proposal. So it was like we met exactly what we wanted to see, and we started a collaboration with both Rafael Lopez and Jan Dalibart. And well, they just found that this was actually possible because typically when you have a two-component supersolid and you have two hyperfine levels, you have one limitation that is the so-called dipolar relaxation, which means that when you have one component in the, let's say, a state -8 and the other in -7, the -7 can decay into -8. And due to dipolar relaxation, which means that you would have a lot of losses. But they found a very sweet spot in the magnetic field in which this dipolar relaxation was incredibly reduced by several orders of magnitude. And they actually proved the fact that they could produce a mixture of two dipolar components in different hyperfine levels. And we started this collaboration, and we have the first results that support the existence of double supersolidity experimentally, in which, well, you see here that you can have the unmodulated state, and here you see these two peaks at the sides, right, which corresponds to this is in the time of flight, which means it's a momentum distribution, and you have a population of these two sides, right, which means that you have some periodicity. And well, these are just the conclusions of what I've presented today. And well, these are just Daniel and Luis, the people with whom I collaborated, and thank you very much for your attention.
So, time for questions or comments? Maybe you can start, of course.
Yes.
Thank you for the talk. I haven't seen how important is this those quantum fluctuations on it. Do you mean if you remove this term, do you lose the supersolid? I think.
Yes, yes, you do.
This is strange.
No, it's because the can I write? There. Okay, I will pick a couple and see. So when can you see? So when you have this kind of state, some kind.
If you write in, the other people on the with the camera perhaps can see. Well, I don't know if they can see something.
So sorry.
Okay.
So when you have this kind, I think it's not working very well. Okay. When you have this kind of dispersion, this dispersion can be broken down, and eventually you get this, right? But when this goes negative, then you start to have a state of negative energy, and you start to decay, right? But this is something that cannot that breaks your system. This is what is called the collapse. You start to see the collapse, and this kind of collapse is produced by the emission of what are called the P waves and so on. However, this is prevented thanks to the quantum fluctuations, because this kind of collapse is essentially making the system to implode. So the densities start to become very, very high. When the densities become very high, when you have a term in the energy that scales with the density to the 5 halves, this is starting to punish this collapse. This punishes the collapse and it prevents it from happening. And at some point, it stabilizes your system. That's why these quantum fluctuations are extremely important. Otherwise, you cannot have a supersolid. It would explode
Okay.
or implode.
In principle, higher order nonlinear terms in the Hamiltonian will also stop it.
Exactly.
Without.
Exactly. Yeah, because the point is that the interactions, the mean field interactions would become negative. So you would have a negative term that goes like this, with something like this. I mean, of course, this depends on the geometry, right? Because it's not isotropic, because it has the dipolar term. It depends on the angle and so on. But this will make essentially very favorable just to make the energy bigger, the density bigger and bigger and bigger and bigger, because it's reducing the energy. That's why you need an extra term that has a bigger power, like the quantum fluctuations, and it's positive. And this is exactly what quantum fluctuations do.
Okay.
Thank you. So my comment is about Wigner crystallization. I don't know if you are familiar with this.
I've heard the name.
Wigner crystallization of electron gas. Wigner crystallization, the electron gas, electrons at very low density on a surface, they also crystallize in a lattice. And my question is the same phenomenon or
I'm not fully familiar with Wigner crystallization, so I would prefer not to say not to say anything I don't really know.
This has not been interpreted as supersolidity of the electron.
I've never seen anyone connecting it to Wigner crystallization, but maybe it's because it's very recent.
On the surface of helium, electron gas on the surface of helium crystallize.
Yeah, but this is not a surface effect. This is a bulk effect. There's an effect in the bulk.
Well, it's an extended to the system.
Well, sorry, you're talking about the Wigner or
the Wigner crystallization? Yes. Well, okay.
Okay, yeah, I really don't know the answer. Sorry.
I think the answer is related to another question I wanted to tell to you, is that how many atoms, what is the expected number of atoms inside each droplet? I mean, I understand this is what in classical physics is called cluster crystals. So
yes.
What is inside, what is in the elementary unit is not one atom or one molecule, but is a liquid.
Exactly.
I think, and this is what is called cluster crystals, and I think this is the case. So just confirm to me, if you have many atoms in each droplet, is this in the Wigner crystal, you have one electron in each droplet. This is the difference.
The number of atoms in each droplet, let's say, it can go more depending on the parameters, on the interaction parameters. It can go from 5,000 to 20,000. This is more or less the atom number we're talking about.
Okay, maybe just two short questions myself.
Yeah, sure.
Motivation to go into two. Apart from this phenomenon you have been mentioning, this catalyzation, one catalyze, the other uncatalyze, are you considering to look if there is an entanglement or quantum correlation between the two things, or?
Well, one of the interests of going into two is because, first of all, when you have two components, you also have, you can have different interactions in the two. For example, one of the things that we are also trying to do is the fact of having to go into the anti-dipolar configuration. In the anti-dipolar configuration is just to reverse because for one component you have this that this is attractive, this is repulsive, right? But when you have two components, the anti-dipolar configuration means that in one component, in the same component, this is attractive and this is repulsive, but with the other component, this is repulsive and this is attractive. And these can actually lead to self-bound drop crystals. To have something that is completely self-bound, that you didn't need absolutely no trapping in order to create it.
So you're more into dynamical effects than in quantum fluctuation.
Yeah, it would be something completely self-sustained. It would be like a droplet, but it's a crystallized droplet. It would be like a new state of matter somehow.
And the other question was if there is a regime in which you can go because you have the Bose-Einstein condensates, and then you have the droplet phase, and you have like this intermediate super solid regime. Is there a situation in which you can jump between one and the other without this transition? And so my point is, every time that I see a transition region, I have the feeling that there is some parameter that you can scale and the transition disappear. And then my question is related to that. Or this is something that is not related.
As far as I know, I would say no, but I mean, I'm not going to categorically say it's impossible. But but as far as I know, I think the answer is no.
Okay. More comments or questions? If not, let's thank Albert again. And I understand he's at the university, and
Yeah.
so we can have more chance to discuss.
Also, el Wiener Crystal, se dice que la estructura es hexagonal. En dos dimensiones también. ¿Es verdad?
No, es triangular.
Rectangular.
¿Es rectangular?
Triangular.
Ah, triangular es hexagonal.
Bueno, vale, sí.
Triangular es
Sí, sí.
La diferencia es que tienes cada onda no es un átomo. Una molécula.
Sí, sí, exacto.
Por eso se llama gota, ¿no? Que dentro tiene.
Exacto, sí. Sí, sí.
Vale. ¿Planeas seguir, Chao, Emilio, planeas seguir con estas líneas o?
Sí, esa es la idea, sí. Esa es la idea.
De grupo alrededor de esto.
Sí, bueno,
La motivación del IAC3, que no hace, o sea, ¿cómo ha sido cuando lo ha presentado la charla? ¿Había alguien que
pero prácticamente no vino nadie.
no vino nadie?
Sí, no, me sentí un
O sea,
poco,
él está preocupado
me
que ellos fueran pocos.
me sentí un poco insultado, sí. Me sentí un poco insultado. Había, no sé, 7 personas.
Ah, vale. Bueno, 7 incluyendo los valores, ¿no?
Bueno, 7 incluyendo a todo el grupo.
Vale. Aquí.
Mm. Ay,